Quasi-hereditary algebras, lecture 12, tilting modules. Let us start with the setup. Let K be an algebraically closed field. Let A be a finite dimensional K algebra with a fixed order on the set of simple A modules. So we have simple A modules L1, L2, and so on, all the way up to Lk. So we fix a linear order on this set of representatives of the isomorphism classes of simple A modules. And we assume that our algebra A is quasi-hereditary for this order. In particular, we have the standard modules delta I for each I, and this delta I is defined as a quotient of the indecomposable projective cover Pi of Li, modulo the trace in Pi of all projectives Pi plus 1, Pi plus 2, and so on, Pk. We also have the costandard modules nabla I, which are defined as the intersection of the kernels of all possible homomorphisms from the indecomposable injective envelope II of Li into the injective modules II plus 1, II plus 2, and so on, all the way up to Ik. Then we have the category F delta of all modules with standard filtration. This means all modules which admit a filtration with standard subquotients. And we have the category F nabla, and this is a category of all modules with a costandard filtration, that is, a filtration whose subquotients are costandard modules. And the main result of the previous lecture was the following theorem, which gives various alternative descriptions for the categories F delta and F nabla. First, about the category F delta. The category F delta coincides with the category of all A modules for which the first extension into all costandard modules vanish. Also, the category F delta coincides with the category of all A modules for which all extensions of positive degree into all costandard modules vanish. Then, F delta coincides with the category of all A modules for which all first extensions into all modules with costandard filtration vanish. And finally, the category F delta coincides with the category of all A modules for which all extensions of positive degree into all modules which admit a costandard filtration vanish. We have dual descriptions of the category F nabla. F nabla coincides with the category of all A modules for which all first extensions from all standard modules vanish. Also, F nabla coincides with the category of all A modules for which all extensions of positive degree from all standard modules vanish. Also, F nabla coincides with the category of all A modules for which all first extensions from all modules with standard filtration vanish. And finally, F nabla coincides with the category of all A modules for which all extensions of positive degree from all modules with standard filtration vanish. Now we can define the main protagonists of the present lecture, and these are the tilting modules. Definition: a tilting module is an A module which belongs both to F delta and to F nabla. So the intersection of F delta and F nabla is usually called the category of tilting modules, and this is a full subcategory of the category of all A modules, of course of all finite dimensional A modules. For example, the simple module L1 is by definition both the standard module delta 1 and the costandard module nabla 1. So this is a tilting module. Example 2. Any projective injective A module, of course if such a module exists, is a tilting module. Because being a projective module, it belongs to F delta, and being an injective module, it belongs to F nabla. there is no reason why a mod should have non-zero projective-injective modules, but if such modules exist, they all are tilting modules. Note that if we have two tilting A modules M and N, then all extensions of positive degree from M to N vanish. This is because M belongs to F delta, while N belongs to F nabla. That's just the consequence of the X orthogonality between F delta and F nabla. Also, the intersection of F delta and F nabla is an additive category, and it is idempotent split, because both F delta and F nabla are additive idempotent split categories. Okay, so here is the main result of this lecture. It's a theorem which is due to Ringel, and it provides a complete classification of tilting modules for a quasi-hereditary algebra. Claim 1. For each I between 1 and k, there is a unique indecomposable tilting module Ti, such that delta I is a submodule of Ti, and the quotient of Ti by delta I has a delta filtration. Claim 2. The multiplicity of delta j in Ti is non-zero only if j is less than or equal to I, and the multiplicity of delta I in Ti is 1. And claim 3. Any indecomposable tilting A module is isomorphic to Ti for some I. In other words, we have exactly k pairwise non-isomorphic tilting modules over A. So this is proved in the paper by Ringel, which is called The Category of Modules with Good Filtrations over Quasi-Hereditary Algebra has almost split sequences, and this paper appeared in 1991. To prove the main result, let us start with the construction of tilting modules. The idea for the construction is that we start with delta I, and we repeatedly universally extend it by other standard modules until we get a module for which all first extensions from standard modules vanish. And then, due to our description of F delta, such module must belong to F nabla. First of all, let us note that the first extension from a delta j to delta I is non-zero only if j is smaller than I. Indeed, assume that j is greater than I. Next, we note that we may assume that j is equal to k due to our homological fullness. So if we look at delta j and delta I, all simple subquotients which appear in these modules are of the form Ls, where S is less than or equal to the maximum of j and I. So we can restrict to the Serre subcategory generated by L1 and so on up to the maximum of j and I, and this will be a quasi-hereditary algebra, and its module category is homologically full in the category of A modules. So we can just restrict to this category, and this means that we assume that j is equal to k. But then in this case, delta k is equal to pk, so it's projective, and so the first extension from a projective module clearly vanishes. So this proves our lemma. So now we do our construction. We start from the module delta I. Let's denote the starting module by n0. The first case is the case when all first extensions from all delta j's to delta I vanish. Then, due to our characterization of F delta and F nabla, n0 belongs to F nabla, and so we are done. If the condition that all x1s from all delta j's to delta I vanish, if this is not satisfied, then of course there exists a maximal j such that x1 from delta j to delta I is non-zero. By the previous lemma, we of course have that j is strictly smaller than I. So we consider the finite dimensional vector space of all first extensions from delta j to delta I, and we can pick some finite bases in this vector space. Let's call it alpha 1 and so on, alpha m. For each element in this basis, we can consider a corresponding short exact sequence which realizes the extension of delta j by delta I with the middle term ks, and which corresponds to our basis element alpha s. Now we take the direct sum of all these short exact sequences and we get the short exact sequence which is a direct sum of them, and we form the following push-out diagram. We consider the diagonal map from the direct sum of m copies of delta I to delta I, and then we have the identity map on the direct sum of m copies of delta j, and then here in the middle we have the push out of this map from the direct sum of all delta i's to the direct sum of all these ks's, and this codiagonal map to delta I. So let's denote this push out by n1. Then, by construction, x1 from delta j to n1 vanishes. And also all x1s from all higher deltas, from delta s where s is greater than j, to n1 also vanish, because these x's to delta j vanish because s is greater than j, and they vanish to delta I because j was maximal, for which x1 doesn't vanish. And now we can proceed inductively. Again, we look at our n1 and look at all deltas for which there is a non-zero x1 from delta t to n1. If such t doesn't exist, this means that n1 has a co-standard filtration, and we are done. If such t exists, we take the maximal t for which x1 from delta t to n1 is not zero, and we just do the same thing as before. We take the universal extension from delta t to n1 and construct n2. After finitely many steps of this inductive procedure, we get some module nr, which has a nabla filtration because all first x from all deltas vanish, and which also has a delta filtration by construction. Moreover, delta I embeds into this nr, and the quotient has a filtration with subquotients of the form delta 1, delta 2, and then all the way up to delta I minus 1. That's due to our lemma from the previous slide. Also by construction, we have that nr has a unique simple subquotient isomorphic to Li. And so it has a unique indecomposable direct summand, let's call it Ti, such that this Ti has Li with multiplicity 1. So our module nr has both delta and nabla filtration, so it is tilting. And since tilting modules are closed undertaking direct sums and direct summands, our module Ti is also tilting. So we have constructed a tilting module with the properties as in the main theorem. Now let us prove that such module is unique. So we know that Ti is indecomposable, and we know that there is a short exact sequence where delta I embeds into Ti, and the cokernel has a delta filtration. Assume that Ti prime is an indecomposable module with a similar property. So there is a short exact sequence where delta I embeds into Ti prime, and the cokernel Ci prime has a delta filtration. Let us apply the functor hom blank Ti to the latter short exact sequence. Note that x1 from Ci prime to Ti vanishes because Ci prime has a delta filtration and Ti has a nabla filtration. So we get a short exact sequence. 0 goes to the hom over a Ci prime to Ti, then hom over a Ti prime to Ti, then hom over a delta I to Ti, and then this goes to 0. Here in the rightmost term we have the natural inclusion of delta I to Ti. Since this map from hom Ti prime Ti to hom delta I Ti is surjective, we can fix a preimage phi of this natural inclusion of delta I into Ti, and our phi is a map from Ti prime to Ti. Similarly, if we do the same arguments with Ti and Ti prime swapped, we get a map psi from Ti to Ti prime, which extends the natural inclusion of delta I into Ti prime. Now note that phi after psi is the identity on delta I being a submodule of Ti, and similarly psi after phi is the identity on the submodule delta I of Ti prime. In particular, neither phi after psi nor psi after phi is nilpotent. But since Ti and Ti prime are indecomposable modules, the endomorphism algebras are local. And if you have a non-nilpotent element of a local algebra, this element is an isomorphism. So this means that phi after psi and psi after phi are isomorphisms, and which means that both phi and psi are isomorphisms between Ti and Ti prime. Consequently, Ti is isomorphic to Ti prime. And this completes the proof of the main theorem. Now we can use the main theorem to define the characteristic tilting module. Definition: the module T, which is defined as a direct sum of all Ti's, where I ranges between 1 and k, is called the characteristic tilting module for A. Here are some basic properties of the characteristic tilting module. First of all, the category of all tilting modules is the additive closure of this module T. That's a direct consequence of our main theorem. Second, the characteristic tilting module is self-orthogonal. All extensions of positive degree from T to T vanish. The third property, the category of delta, can be described as a category of all A modules for which all extensions of positive degree into the characteristic tilting module vanish. Similarly, F nabla can be described in the category of all A modules for which all extensions of positive degree from the characteristic tilting module vanish. So, as we already mentioned, the first property follows directly from the main theorem. The second property is just a consequence of the extra-orthogonality between F delta and F nabla, because T belongs to both. So we will prove the fourth property, and the third property is similar. So let us prove property 4. First of all, let us note that if some A module is such that all extensions of positive degree from all standard modules into our module N vanish, then of course all extensions of positive degree from any tilting module into this module vanish. This is because T has a delta filtration. So we know that the first category is just F nabla, so in order to prove property 4, we need to prove the converse inclusion. That is, if we have an A module N for which all extensions of positive degree from all tilting modules vanish, then all extensions of positive degree from all deltas vanish. In order to prove this, let us apply the functor hom A blank to N to the short exact sequence from the definition of Ti. So delta I is a submodule of Ti, and the cokernel Ci has a delta filtration. In the long exact sequence, for each m, we have the following segment. So we start from the degree m extensions from Ti to n. This goes into the degree m extensions from delta I to n. This goes into the degree m plus 1 extensions from Ci to n. And this goes into the degree m plus 1 extensions from Ti to n. Now we assume that n is such that all higher extensions from tilting modules into n vanish. So the first term and the fourth term in this segment, they are 0. Therefore, from the exactness of the sequence, we get that the degree mx over a from delta I to n is isomorphic to the degree m plus 1 x over a from Ci to n. Next, we note that Ci actually has a filtration with subquotients delta 1 and so on, delta I minus 1. In particular, C1 is 0. But this implies that all degree mx from delta 1 to n are 0. But then this implies that all degree mx from C2 to n are 0. because C2 has a filtration with subquotients delta 1. But then this implies that all degree mx from delta 2 to n are 0 for all m greater than 0, and so on. So by induction, we prove that all extensions from all standard modules into n vanish. Of course, all extensions of positive degree. Let us look at one example. Consider the path algebra A of the following quiver. We have vertices 1, 2, and 3, an arrow from 1 to 2, and an arrow from 3 to 2. The path algebra of this quiver is hereditary because we don't have any relations, and so it is also quasi-hereditary. Since this is a type A Dynkin quiver, we have 6 indecomposable modules. The first module, which is concentrated at the vertex 1, that's a simple module L1, which also coincides with delta 1, nabla 1, and with the injective module I1. The simple module L2, which is concentrated at the vertex 2, coincides with P2 and with delta 2. The simple module L3, which is concentrated at the vertex 3, coincides with I3 and nabla 3. Next we have the projective P1, which lives at the vertices 1 and 2 with the identity met between them. This coincides with nabla 2. Then we have P3, which is supported at the vertices 2 and 3 with the identity between them. This coincides with delta 3. And then we have the indecomposable projective I2, which lives at all vertices, and both arrows are the identity maps. So now here we see that the tilting module T1 is L1, which is delta 1 and which is nabla 1. This is always the case. The smallest simple module is tilting. Next, the tilting module T2 is nabla 2, which is the same as P1. So here we have nabla 2 and P1. So being a nabla, it has a nabla filtration. Being projective, it has a delta filtration. So this is why this is a tilting module. And the tilting module T3 is just I2. So here is the module I2. That's a module which is supported at all vertices. So being injective, this module has a nabla filtration, and it also has delta 3 inside it. So here is delta 3, and the quotient is delta 1. So this module is nabla filtered because it's injective, and it has delta 3 as a submodule, and delta 1 is a quotient. So it is in F delta. And for the remaining modules, we see that L2 here, it has no costandard filtration because nabla 2 is bigger. Then L3 has no standard filtration, so L3 is a simple module where the standard at 3 is P3. And finally, P3 has no costandard filtration. The module P3 is delta 3, so it's delta filtered, but it doesn't have a costandard filtration because nabla 2 also has something at the vertex 1. So here we see that we have 3 tilting modules, and these are the simple at the vertex 1, and then nabla 2, and then the module I2, which is supported at all vertices. So here is one more interesting homological property of tilting modules, and it's the relative injectivity of tilting modules in the category F delta. Theorem: for any object M in F delta, the object M has a finite coresolution by tilting modules. In other words, there is a finite exact sequence. 0 goes to M, then to Q0, then to Q1, and so on. Qm goes to 0, where all Qi are tilting modules. Proof: for any module M in F delta, let us denote by bold M of M the maximal I for which delta I appears as a standard subquotient of M. Note that if the bold M of some module is 1, this means that our module has only L1s as composition subquotients, and so it is a tilting module because L1 is a tilting module. Therefore, to prove our theorem, it is enough to show that any module in F delta can be embedded into a tilting module such that either the cokernel is 0 or the cokernel is in F delta and has strictly smaller invariant bold M. So bold M of the cokernel is strictly smaller than bold M of M. If we can do that, we can do it repeatedly, and at the end we make this bold M invariant equal to 1, and so the cokernel will be a tilting module. So let's prove only this claim that any module with a standard filtration can be embedded into a tilting module such that the cokernel is either 0 or has strictly smaller bold M invariant. So if M is the standard module delta I, then we can embed delta I into Ti. The cokernel is filtered by smaller deltas, and we are done. If M is not a standard module, then M has a standard filtration, so we can embed some standard module delta I into M, such that the cokernel has a delta filtration. By induction on the lengths of the delta filtration, we have that the cokernel can be embedded into some tilting module Q, such that the cokernel, so Q over C, has a delta filtration, and the bold M invariant of Q modulo C is strictly smaller than the bold M invariant of C. Also, we embed delta I into Ti, and we claim that this can be lifted to a map from M into Ti. Indeed, we apply the functor hom over A blank Ti to our short exact sequence, and since Ti has a nabla filtration, we will get a short exact sequence, because x1 from the cokernel to Ti vanish, and so we can lift the embedding from delta I to Ti to a map from M to Ti. And therefore, we can embed M into Ti, direct sum with Q, and the cokernel of this embedding will have a delta filtration. And by construction, the bold M invariant of C prime will be strictly smaller than the bold M invariant of the original module M. And this completes the proof. So now we can revise and emphasize some properties of the characteristic tilting module. So first of all, the characteristic tilting module has finite projective dimension. That is easy because A is a quasi-hereditary algebra, and so it has finite global dimension. Any module has a finite projective dimension. Property 2, the characteristic tilting module T is self-orthogonal. We already mentioned it, so all positive extensions from T to T vanish, because T belongs to F delta and F nabla, and we have the X-orthogonality between F delta and F nabla. And finally, from our previous theorem, the left regular A module A, it's projective, so it's an F delta. It has a finite co-resolution by tilting modules. A module which has properties 1, 2, and 3 is usually called a generalized tilting module from the point of view of general tilting theory for algebras. So there is some confusing terminology here. A tilting module for a quasi-hereditary algebra is a generalized tilting module in the sense of the general theory of tilting modules for finite dimensional algebras. So let's do one example. So we take the same example as before. We take the path algebra A of the following quiver: vertices 1, 2, and 3, an arrow from 1 to 2, and an arrow from 3 to 2. So, and this algebra A is hereditary, and so quasi-hereditary for any order. We have the natural order on 1, 2, and 3, and it has 6 indecomposable modules. The simple at 1, which is also tilting, because it's also delta and nabla. The simple at 2, which is projective and delta. The simple at 3, which is injective and nabla. The projective at 1, which coincides with nabla 2 and hence also is a tilting module for the vertex 2. The projective at 3, which is delta 3. And the injective in 2, which is a tilting module for 3. And here we can see that the projective at 1 is the tilting module at 2. And so if we embed P1 to T2, we have the tilting co-resolution of P1. Now P2 embeds into T2 and the cokernel is T1. So the tilting coresolution of P2 is T2 goes to T1. And finally, P3 embeds into T3 and the cokernel is T1. So P3 embeds into T3 and the cokernel is T1. So here we have all tilting coresolutions of all projective modules. Moreover, we have two more modules which have a delta filtration, namely delta 1 and I2, and both these are in fact tilting modules, and so the tilting coresolutions are trivial. So the only indecomposable which is not in F delta is L3. But this module is not a submodule of any tilting module. So if you look at this is L3, this is T1, this is T2, and this is T3. And L3 is not a submodule of any of them. So it's not a submodule of any tilting module, so it cannot have any tilting co-resolution. Let us finish with some problems and questions. Problem question 1. Prove that an element of a local finite dimensional algebra is invertible if and only if it is not nilpotent. Problem question 2. Prove that F delta coincides with the category of all A modules for which all extensions of positive degree into all tilting modules vanish, with all details. Problem question 3. Prove that Ti surjects onto nabla I, and the kernel of this has a costandard filtration with subquotients nabla J, where J is strictly smaller than I. Problem question 4. Prove that any module in F nabla has a resolution by tilting modules. And problem question 5. Compute all indecomposable tilting modules over the path algebra of the following quiver. We have vertices 1, 2, and 3, an arrow from 2 to 1, and an arrow from 2 to 3. Thank you very much and see you next time.